few more people will show.
Oh, it's a quiz?
If you like, you can make it a quiz. So, the goal of the meeting today is you see two pieces of paper. The one which is called homework and one that has nothing. So the one which has nothing will be for now. So we should fill it before the end of the meeting, and the one which is labeled homework you can take and enjoy later during the weekend. It's not urgent, right? So I'll explain what is there. We will be filling it maybe during the last 5 to 10 minutes of the meeting. So who we are and what are we doing? So it is a course in computational chemistry. We want to characterize the properties of materials and molecules through computational modeling, and we are in the end of the first chapter. So originally we started from setting up operator of total energy with contributions from electrons, nuclei, setting up distances, momenta, and setting up molecular Hamiltonian that enters into molecular Schrödinger equation. And then we realized that it has too many degrees of freedom and started to divide and conquer, to split electronic and nuclear degrees of freedom. And after we accepted, okay, I'll take the words. After we accepted that electronic parts of Hamiltonian can be separated and assume that nuclei are fixed, one can find solutions for electronic degrees of freedom and use these electronic wave functions as basis, find overall total Schrödinger solutions of molecular Schrödinger equation. And this sets up forking to point to split electronic and nuclear degrees of freedom, and further one can think that nuclei are very not time independent but time dependent Schrödinger equation, and then if we are focusing on observables like positions of ions, one can practice Ehrenfest theorem through Heisenberg equation of motion and set up equations that look very much like Newtonian equations, but they are for expectation values of each position of each nucleus. So they carry on information about quantum properties of electrons, quantum properties of nucleus, with non-adiabatic couplings neglected. Right? And by now, we do have this set of equations for positions and for momenta that may change in time. Right? So why do we need them and what do we want to do with them? One can try to solve them numerically and find trajectories of molecular dynamics, which is cool. But prior to doing this, there was a practically important task of so-called optimizing of geometry, finding minimum of potential energy surfaces when atoms experience minimal forces and potential energy has minimum. So we are going to discuss how these equations for expectation values of position lead to an algorithm of finding best optimal interatomic distances. In some sense, you will hear nothing new today. It will be the same information we discussed before, but it will be watched from a different angle. Before we were looking on theoretical background and more abstract academic approaches, today we will be a little bit more practical. We will consider how these equations can be solved in the algorithmic way. Like each equation can be solved either by derived equations, like integrating, differentiating, giving answer formulas, which is cool. But if you have 1,000 atoms, maybe not quite possible. And another way is to solve something numerical. And if we solve an equation numerically, we need a code that implements some ideas, some algorithms, some steps. And we may set up this list of steps that is needed to solve the positions that will incrementally approach the best geometry. So on the in the table you have columns and rows, and this rows will correspond to different steps, like time steps or optimization steps, and we will pretend that each of us is a little computer with a robot that tries to solve optimization problem. And before we go to this, I need to mumble some equations and some flowcharts, but we will play robots today. So, Yancha, did you submitted any jobs on CCAST before? You?
Yeah, yeah, it's me. Yeah.
Oh, sorry. I need to learn very better. Did you submit jobs on CCAST before?
Yeah.
Can you add it to your presentation?
Okay, no problem.
Oh, thank you. And I'll ask Steven if he wants to add this command for downloading files. And then we will cover everything except Vesta, which, if no one is interested, probably it is not needed for your research. If anyone is interested, you feel free to add, but it's optional. The concept of X-ray diffraction for given geometry. Yes, we will fill one table in class and another table you will try to fill at home. But it is due in a week from now, so do not rush. Presentations are more important. Does anyone want to submit previous homework? Did you bring it? Or I've heard someone send it by email, but if anyone had it printed. It will be a little help for me to give the lecture.
My this often statements via email.
Absolutely, absolutely. Yep. Yes. What?
Do we have homework?
Yes, we do.
Oh, so what's the due time?
Tuesday in class. Right now.
Right now?
Well, do not worry. There will be more homework.
So could be something Thursday?
Yes.
But
if you need to prioritize, presentations are much more important. If we all are targeting good grades for everyone, but if you really want to count each penny, the credit for presentations is like 8 times bigger than for the whole work.
So could we for the rest of semester put the due time on the Thursday? So during the Tuesday or Wednesday we can ask the questions or some it's more.
I'm flexible about this, but it will be not optimal for the materials because homework is designed to help next lecture. And I really like emails. Please send me and ask questions about homework by emails. I do not promise answering immediately, but I promise I will read everything and answer to my best ability. It is what we are doing. So, and it is what we were doing last time. So we do have our training in the part, and then through the theorems we are working now with expectation value of position and force for this position, which can be explained in both through expectation value of the derivative of the electronic part of the Hamiltonian with respect to change of the position. And then if we practice it, we will get two equations which are equivalent to Newton's equation of motion. So acceleration of each degree of freedom of each nuclear coordinate is equal to force over mass, right? So now I'm looking on the now I'm looking on this equation and trying to identify what we can do and what are the terms, how can we analyze it. So the reason to change position, well, I will skip the words expectation values, but we always have them on our background. The reason to change position is non-zero momentum. And the reason to change momentum is non-zero force. And the force is expectation is derivative is gradient.
Energy
Should be
position, right?
Yes, thank you. Thank you much for correcting immediately. Yes. So derivative of potential energy surface in respect to position of nucleus, right? In case, and there is another approximation for today's lecture only. It is absolutely clear that any practical model except diatomic molecules will have a lot of interatomic distances, a lot of Cartesian projections, a lot of nuclear degrees of freedom. But if we would try to consider reasonable natural systems as an example, it will be too much effort. We will select only one nuclear degree of freedom, which can be either interatomic distance in diatomic molecule, H2, or it can be selected preferred degree of freedom in a smaller molecule which doesn't depend on other degrees, like maybe two molecules supplemented by one bond. So, in case the force will be zero, momentum will not change. If initial momentum is zero, which means zero temperature, position will not change, right? So if you find such value of position when this derivative equals zero, when the force is zero, it means that the system will like this nuclear configuration very much. It will not try to go anywhere away from it. Its best optimal position. And we want to find a procedure that will select among all possible interatomic distances such one that will provide the zero of this derivative. If you would do analytical solution, we can solve. So if you have equation for potential energy surface, we can solve this equation and find at which values of the interatomic distance this equation will be satisfied. But the potential energy surface the forces will be numerical data in tables. We are not going to have formulas for multidimensional surfaces. It will be only numerical data, and setting up a derivative and finding the optimal distance in the analytical way is quite impossible, except very, very simple cases. So I'm going to navigate us to the two possible ways to solve this problem, and then select, maybe we together can select which strategic direction is better. So for each arbitrary interatomic distance, we always can find the value of potential and value of the force. And there are two ways to find this minimum. One is to scan all possible interatomic distances and reconstruct potential energy surface. Maybe make feeding with a spline, and then process this analytical search of the available surface. Another way is walk of a blind man, or analogy. Did anyone play computer games? Don't hesitate. Yes? Okay. Which games did you play? I do not know modern trends. I know what were trends like 30 years ago, like Doom.
Super Mario.
Did you play any strategic games? Or there are several figures and the area is covered by fog of war, like nothing is seen, but when your figures are moving, the map is becoming open, right? So the figure, the character, your thing that you manipulate doesn't see the landscape until it moves somewhere. So one can practice the same idea in finding optimal interatomic distances for molecules. So suppose that our molecule currently has certain distance, and it doesn't know, it knows what is the potential, it knows what is the forces on each atom, but it doesn't know what will be the forces if we move to a slightly different interatomic distance. In order to find what will be the potential and force, one needs to elongate or construct distance and slowly recover the fog of war, slowly recover the potential energy surface. And if we take this second direction, then we can find an algorithm that will not recover the overall potential energy surface, but will recover only the path that eventually will bring us to the minimum. So we need a smart design of a path. Like if you are on a hill, we need to find a path that will lead us downhill, right? You don't need to know all potential surface. You just need to go down all the time, okay? And among these two ways, reconstruct the whole potential energy surface or reconstruct a path that leads to a minimum. Which one do you prefer? I hear the voices, the path. I agree with you. It's what majority of tools is doing. It's something that you know, just a little reminder that you may use later. Maybe I believe that each of you can come to the board and explain. Right? If this is Newton equation, right? Acceleration somewhere should be mass. and the force, which is the derivative of potential energy surface. Then one can solve it and find that the increment of the position at next time, is what it was before, plus a term that propagates a little bit forward in time according to the velocity, to the momentum, right? And then another term that propagates according to square of the time and according to the force, to the acceleration. Please ask a question if you do not feel comfortable. Yes?
What is the symbol, the first delta, and this equation? So the minus the it's fine.
Oh,
Yeah.
it's my poor calculating. It's d2 or dt squared. D2, yes.
Second. Oh, second derivative. Okay.
D2.
Thank you.
Okay. And are you comfortable with this stuff?
How these equations come? It's data symbol.
If you integrate this differential equation, integrate it once, then it will be first derivative here and integration over time there. Integrate twice, it will be two integrals here and addition here. So from the first integral, and in case you propagate in time by infinitesimal time, if we are going forward by very small time, then instead of integration, it will be just multiplication, like the integration in infinite differences with only one step. And this proportion to t comes from the first integration and square from the second one. Enough?
Just to clarify on that equation, so when you have are the two lines one equation? So are
just navigating, where should I go?
no going down? Yes. If you continue, does it continue to potential time? Is that continuation?
Yes, it's
All right.
continuation.
So it's RT plus potential function T over M.
This is P, momentum.
Yeah, momentum.
Like this one would, I think it is one of the classes in this wrote in the previous year. If you already have it, you don't need to write it over. If you throw something in the free acceleration on the surface of Earth, then this the potential of any mass is in GH. H is altitude, and if you take you can take mgr. And if you take derivative over r, and mass should be somewhere contracted, it will be g, free fall acceleration, right? So this comes very close to just mechanics of the free fall acceleration, same things.
Oh, so we don't consider the mass.
We should. Let's fix it. So it should be 1 over m. So, So the force that comes here is derivative of position, gradient of of the potential energy source. Here is most important equation that we will utilize when we will play robots. Suppose we do know the interatomic distance at step I and step I plus 1. So we did make one step in this computer game or in the procedure of optimizing distance. And then at step I, the value of potential energy is U sub I. At step I plus 1, it is U of I plus 1. Then this ratio of increments will be expressed in finite differences. Right? So as soon as we have one step, we can find the force. And this is a solution of the Newton's equation if time is very short. If it is not short, if it is long time, it will be integrals. But if in the vicinity of small change of position in time, the force can be considered constant, and the integral will be just t squared over 2. So we want to merge this solution of Newton's equation and the finite differences for the force. If you drop something, it finds local minimum. It finds a position when energy is minimized, right? But it finds this position in case there are, it will go to this direction if there are no initial velocities. If I throw it up, it will not go where it should go. Also, there is, if we solve equations numerically by large steps, if our step, if you do things in the finite differences, the size of the step is not always optimal, is not always small enough. Sometimes we need to make bigger steps. And then errors accumulate. And one of the possible errors that we can easily interpret is that we overestimate, like if I'm throwing something and instead of being stopped by the force from the substrate, it will break it through and go over. So if we use too large of the time step, this is a typical error. And in order to avoid such errors, to minimize it, one may want to put an artificial damping in front of these terms. So it will not change overall direction, but it is just a little trick to quicken the conversions. If you're not quite comfortable with this idea, I want to share what I was reading as a teenager. You all know right now there is an effort to make cars driverless, right? Autopilot. There is a cruise control that keeps the velocity, and there is a lane departure system that if driver tries to cross the drawn lane, it will return it back. And for everyday people, it is quite a new concept. But in like more larger projects like space exploration or military applications, it was used for a long time. So suppose, and what I'm talking right now is illustration. You can just lean back and relax. I'll tell you when to concentrate better on the class material. Suppose you are launching a spacecraft, and by some random factors, by asymmetry of the construction, it will not go straight up as it should, but it will start to deviate. And if you do not steer it in the opposite direction, it will just fall down. So one needs to have the accelerometers find if it deviates and then turn opposite direction. So the very early versions of these automatic steering devices were doing like, if the craft is deviating in one side, one needs to steer in the opposite direction the same manner. And then it deviates and comes to the opposite direction. Then one needs to compensate it again, and then it goes to the opposite. And then it starts oscillating, going on a crazy trajectory. But if one steers it in the, after detecting the deviation, steers it in the opposite direction in a halfway, then it just returns to the straight thing. Okay? So therefore, we put a small parameter between 0 and 1 that will go not as a regular force, but a little bit smaller. And there are different implementations of this idea, but one goes into the direction prompted by the gradient, but a little bit slower than in the true molecular dynamics.
Also, after one question is after adding the dynamic parameter, it will not decrease the, it will not reduce the time step, just pulling back in the wrong direction.
It prevents it from going into the wrong direction. It will stop before one goes too far. Okay, so some of you have successfully submitted homework in time. And one of the questions was to find online an image of the potential energy surface and write something about it. So I took it from this book. If you haven't done it, you can find it and use it for the homework. Just make a screenshot and find it online. So if you have more than one interatomic distances, the potential surfaces can take complicated shapes, and there are standard there is a standard language to call the features of the surfaces. So the lowest possible point is local minimum that we want to find, but there could be several local minimums, and there could be maximum and center points. For the chemistry language, one can call the local minimum reactant, global minimum product, and saddle point transition state, right? And we were discussing two options. One, to create potential energy surface in numerical way and then just explore and find the minimum. And another one is to find the trajectory, going from initial interatomic distance to the first, second, third, and then to the optimum, right? Find a path that leads to the global minimum. Okay.
So usually potential energy surface is randomly
It's not random. There is a big chemistry about its profile. Like if for something that is stable, it is minimum. For something that is unstable, it is maximum or it is higher. And there are several transition states. If we want to abandon any chemistry, like if you hate chemistry, but you like materials, you can think of a solid surface that is getting a small molecule that is getting absorbed, right? And there are several surface atoms. Like when the molecule is very far enough, it's probably like energy is high. And then there are several absorption sites where molecule like to be attracted to, and other site where it doesn't like to be attracted. And when the molecule travels on the surface, it experiences going up in energy, going down in energy. So it's not random. There is a background for this profile. But for any molecule, for any reaction, for each surface and substrate, this profile will be specific. And in most practical cases, it's much more than 2 independent degrees of freedom. It's multidimensional that humans cannot imagine.
Yes. So this profile is only determined by the number of molecules or the interaction between different atoms?
Interaction between atoms. And here's a little although everyone suggested and agreed that finding a path is much better than reconstructing the whole potential energy surface, just in case if someone is still doubting, a little example. So suppose we split our possible values of interatomic distances onto grid points, and we take very low precision, very rough splitting, only 10 grid points for all possible interatomic distances. Then for diatomic H2, there will be 10 points. And for 10 interatomic distances, we can find 10 values of potential energy, and it will be easy when chemical constructed. If it will be 3 atoms, like water, number of degrees of freedom is 3n minus 6, right? You know this equation. Number of degrees of freedom for a molecule, 3 times number of atoms minus 6, because you subtract rotation and translation degrees of freedom. 3 times 3 minus 3 translation is 3 rotation equals 3. Then for each degree of freedom we have 10 points. 10 times 10 times 10, 1,000 points. It's still possible. 1,000 interatomic distances, 1,000 potential energy values. If we take something humble like etc., n equals 4, 3n minus 6 will be 6. So one needs million points. And if one goes to methanol, still rather small molecule. Yes, I'm making error. Let's really count. 4, 5, 6. 6. Maybe 18. 6, maybe 12. Oop. Oop. So when it's so many points, so it will be a little challenging to so 10 to the 6 megabyte, 10 to the 9 gigabyte, 10 to the 12 terabyte. So we need terabyte only for this one thing.
How do you measure the number of grid points?
I just decided per degree of freedom I use only 10 grid points. Just because otherwise it will be too expensive. But it will be too expensive anyway. So reconstructing potential energy surface is not always good. Gradient cake can be multidimensional. Okay. So we are approaching to the table, and on each step we will need to do intermediate calculations that will lead us to computing the change in the interatomic distance. So this equation comes from solving Newton equation, delta T squared over 2. This one, change in potential energy divided by change in position is with minus is gradient, gamma is damping parameter, and we need to find it. So it is a last thing that we need. Suppose that we went through several steps in this table, and we already find interatomic distance number I. Suppose that we do have a procedure which is not part of our consideration today. If we are programmers, it is a subroutine. If you are mathematicians, it is a tabulated function. If we electronic structure guys, then it is potential energy surface that comes from eigenstate of electronic Schrödinger equation plus Coulomb repulsion of nuclei. Suppose we can find value of potential energy for provided value of interatomic distance. If we have this stuff, and we can find the value of potential at the next step, by subtracting two nearby steps, we can find the change in potential energy, right? And then by ratio of change in potential energy and ratio of the interatomic distances, we get the gradient, right? At this point, I have a note that I need to tell a joke. We are planning to go a path on the potential energy surface. But suppose this path will bring us to a spiral that will circle around the global minimum. And you'll be never exactly there. Can we do this? For entertainment, yes. But for solving practical problems, we need to stop somewhere. We cannot waste computer time. We need either report failure or accept some precision. So the algorithm should stop at a certain point. Now, a time for a joke. A programmer works at a company, and one day he doesn't come to work. The boss, colleagues are becoming nervous, waiting a day, he doesn't appear, waiting a second, he doesn't appear. On the third day, a delegation comes to his apartment, door is open, coming and finding programmer still alive but with blue skin, sitting in a bathtub with shaking hand, looking on a bottle of shampoo. Apply to the hand, rinse with water, repeat. So we want to avoid this situation, not repeat it too many times. Okay, so we kind of have equations, but if we're not going to be programmers, but maybe some of you will be employing programmers. You need to be able to give order, to give like request what needs to be done. Just strategically think, or just shop for code that follows your idea. And if one wants to communicate ideas of programming between people who do not use the same programming language, have no use of any programming language, but still needs to communicate ideas in the algorithmic way, there is a very simple language of flowchart that basically any algorithm can be expressed in this way. In order to draw flow charts for algorithms, I do not need to know any programming language. And it is very short dictionary. Like a line means arrow means transfer of data. The like oval or little disk means like input or output. The rectangular bracket means mathematical operations like implementing one of the equations. And the diamond tells whether to go one way or to another way, choices. And basically anything that our computers are doing can be expressed in this way. It's used to communicate ideas between people and then later to set up codes. So we are going to use equations for gradient and finite difference, for solving Newton equation, and for stopping programmer from sitting in a bathtub, like interruption of an algorithm, in a flowchart language. So we will start from something and then we will go into a cycle, repeating certain procedure several times. And we can check at the very beginning if we already repeating the procedure more than 10 times, it's called a bad algorithm or bad system, and one needs to report failure and stop any attempts. So if we are just doing first step, or if number of steps is less than 10, so we input initial geometry and we need input step size, and we need so-called tolerance. So up to which precision the algorithm will work. So if we come close enough to the global minimum, we should report that goal is achieved. Because absolutely it cannot be done. It can be done only to a certain level. And this is called tolerance. And, often reported with letter. Oops.
I have a question.
Yes, please.
So what determines algorithmic error?
Once again, it's slower.
Oh, what determines the algorithmic error, or how close we can go to the
It is your free will as a human. If you take this tolerance limit too high, and then you look on the output, it will look ugly. If you take it too small, the result will likely be perfect, but it will take too much time. So you, and most computer codes do have pre-made values of this tolerance that set up for a balance between precision and computer efforts. But if you do something exotic, one can go inside the input parameters and modify it to your wish. So, one is practicing everything that we discussed, like square root of the increment time, gradient, and what calls it is computation of the increment. If you have one-dimensional, it can go only forward and backward by certain larger or smaller steps. If it is multi-dimensional, it also shows direction, in which direction to go. Then, what updates? Interatomic distance at the next step will be equal to what it was before, plus this increment. And then, upon making this increment, one computes new value of potential energy surface. And then one computes subtraction of this potential energy surface before and all and new values. If their difference is less than tolerance limit, then the last computed interatomic distance will be your answer. And the last computed value of potential energy surface will be your answer for total energy. we have optimized interatomic distance, or in more general or multidimensional case, you found the geometry of the mode. Right? This is what we did in the what we will be doing tomorrow. Draw something and then finding it in a better shape, because by human hand it will be not ideal when we start drawing. If this condition is not satisfied, we return back and use this value of position and this value of potential as an input for the next step, and try to repeat it again until we get a convergence, or until we go too far. Okay? So, we are going to do a very ridiculously oversimplified COE example, because otherwise it will be very complicated. So, we will take the potential energy of R squared, where we know predominantly that the answer will be R equals 0. But suppose that, let me suppose that I'm a blind robot that can walk over this function only as through fog of war, to recover only one point. I do not, like, I start at a certain point, and I do not know what will be the values of the potential on all other points until I intentionally go to this point and find it. And it mimics realistic situations with multidimensional things. So we need to check if our algorithm will bring us close enough to this 0 point. So I suggest we start with initial position -5. We set this tolerance criterion 0.3, and to start somewhere, we make the first step by size +1, and any increment will be chosen as a square root of 2. But in your homework, you can try different parameters. I know that these parameters will simplify our task in the class. And the damping parameter will be also 0.3. So you may want to write down these values on a corner of your forms.
We are using U plus R squared.
Huh?
The equation.
Yes, yes. U plus R squared. And let's start. So this is the form. Let's start filling it. And I suggest we do it collectively. Like each person will fill one cell, maybe starting from me. So step number 1. The initial position was -5. Suggested increment was +1. So I put here -5 plus 1 equals 4. The previous value of potential energy surface was -5 squared, is 25. 25. Now, present value -4. Right? -4. Present value of potential energy will be -4 squared. How many? 16. Delta U. What will be the increment of the potential energy? Huh? 9.
16 minus 4.
Should be 9.
20.
25 minus 6 is 9.
16 minus and minus gonna be plus, so 20.
Both
It
of
can be
them
plus
are
or minus, but
positive.
still 9. So if we define as mu minus all, 60 minus 25
Minus.
minus 9. Now, delta U divided by delta R is minus sign. Minus 9 divided by plus 1 equals plus 9.
What? Oh yeah.
So minus 9 goes here, plus 1 goes there. Minus cancels with minus 9. So delta t is chosen to be square root of 2. Just simplify our life so that delta t squared divided by 2 will be 1. And now let's compute delta r. So 0.3 then the parameter.
Gamma is the 0.3 here. Is double.
Yeah. That's right. 0.3. We also need a minus. Oh, minus is already included here. So we don't need this minus. 0.3 times 9 times 1.
Divided by.
No divided.
It's out.
How much?
2.7. Minus 2.7.
No. 2.7? 2.7? Approximately.
Minus.
Let's think about minus. I would vote for plus, but I can make errors. So 0.3, and then minus delta U delta R
Minus.
is 9. So it should be plus 2.7. Right?
But why the first delta R is 1?
Just a second. Minus 2.7. Please repeat the question.
Oh, I mean the first delta R. Why the first one is, yes, it's positive 1.
If we do not define what is initial increment, then we cannot make the first step.
Default.
We need to define it. Also, it's our choice as humans. Okay, step number. Step number 2. Previous value was minus 4.
Your call will be disconnected.
Not worry. Minus 4 plus 2.7. How much?
Minus 100.
1.3.
Minus 1.3. Now it becomes too complicated for me. I need your help. So please bring up your calculators. And continue to fill it and just fill one cell. So it will be 1.3 squared, right?
Yes.
Okay. Yeah, please go to the next.
69 minus 16.
Does everyone agree with that?
Yeah, it's correct.
Let's double check. So here we were subtracting 16 minus 25 was minus 9. Okay, yes, I agree. Okay, yeah, thank you. Let's go forward and fill the next letter.
So it's
Escape. Yeah.
minus 4, 31, divided by plus 1, right?
No. Delta R was plus 2.7.
2.7. 2.7. What's the result for?
5.3.
2.7. I will write it this way.
Escape.
Minus 5.3.
Okay.
And if positive.
Oh, it's very bad. How can I write it again?
You want to erase?
No, yeah. This is minus 5.3, right?
Yeah.
Yes.
I write it vertically in the words way.
And thus, yeah, thank you. And the sign should be plus,
Yes.
right? Because the minus is from here.
Oh, sorry.
That's okay. That's okay. Let's. And this is simple. I can do it myself.
This is
So
this is 2.7 is positive or negative? Delta R.
here it was positive.
But
So we were approaching from minus 5 towards minus 4 towards minus 0.3. And we are approaching from negative side, we need to approach 0. And do not go too far up.
Are we assuming delta t to be root 2? How is delta t root 2?
It is our choice as humans. Our choice.
it is step
And
size.
here again will be 1. Now, can you try to have the next one? We will do it only twice. Once in this class and another time at your homework. And all other times it will be done by computer. You just... so what do we put here? So, 0.3 times 0.3 times 5.3, right? So,
Is that correct?
is everyone agrees, or it's a different number?
Yes.
5.3 times 0.3? Not there.
It's a minus.
I'm not sure about minus, but what about
It's
numbers?
positive. It's
The first number is 0.3, right?
Yes. It's
From this guy.
1.59.
Yeah, it's fine.
Okay,
It's positive.
plus. Yeah, thank you.
Okay, thank you.
Won't we
So-
have minus 5.3? Why aren't we using minus 5.3? Because minus tells you that.
No, see,
We have
we
minus-
have here, we have
yes.
minus here.
It is in
This minus goes from here to there.
Oh, okay.
Okay?
Yes.
It's applied in other color.
Can you help for the next step? I feel this so for you because it is easy. So previous step was minus 1.3, and then we have plus 1.59.
Okay.
Minus 1.3 plus 1.5 is 9.
Yes.
Right.
Yes.
Maybe just
You can write to the next lower cell. If you need more space.
It's 0.29. Yeah. And the S squared is 0.848.
how do I calculate the UTI? I forgot.
Square.
S squared.
Just 0.29 squared second level.
Square. Is minus
Okay. Yeah. Thank you. Thank you. Everyone agrees with this number?
Yeah.
Raju?
Correct.
Let's continue. So the previous value of potential was 1.69. New value of potential is 0.084. So when it's previous minus
0.0841 minus 14.31.
no, not 14. Minus 1.69.
Sorry. Yeah, minus 1.6. Can I erase?
Oh, how to erase?
Sorry, 1.6. This can be how much it is? Minus
1.61 approximately, right?
1.61.
Which one?
0.0841 minus
You minus 16059.
minus 1.
Minus 1.6059.
Escape.
0.6059.
Okay.
Correct.
Yeah, thank you. And the gradient.
So we have one, 6. Can I say 6.1 for the?
It's minus 6.1.
Yes.
Escape.
Divided by 1.
Escape. Okay.
series right now.
That's like 1 point.
Yes.
Mhm.
Or it's
Yeah, thank you.
learning rate. This is dumping rate.
And if I
It's
put
optional.
here,
Oh yeah.
Yes.
point 3,
No, should be plus. We have a minus here, a minus here, minus that minus could be plus.
should it be positive, right?
Yes.
Here it's positive.
But we have already considered.
So basically it will be 0.3 with something. 0.3 times
Is
1.
this minus, this term is this. So it's positive and this positive. Totally should be positive.
Oh yeah.
Got it?
And then on the step number 4, I'm using previous 0.29.
So what was there?
29 plus, not plus, times 0.3. No, plus, right?
Yeah.
So there'll be 0.59. So if you go further this way, you see we missed the minimum and went to the positive side, right? They were negative, negative, and now it goes positive. And what we expect if we continue this calculation, the gradient here was always positive, right? It was moving us towards a minimum. Right now, we went the opposite direction, and gradient here will become negative.
And it will come back.
Yes, it will help us to come back. And with one more step, one will have the convergence criterion matched. So here, we were about 1.6, and we need a few times less. As soon as it reaches 0.3, it will be converged. So one of the previous years, we used slightly different parameters, and it did converge on the first step.
So the criteria to finish this loop is delta U, right?
Delta U,
should
yes.
be-
Delta U should become smaller than tolerance limit. Or if you do 10 steps and do not reach success, just stop and report what you did. Okay, I don't know what else. We stopped a little too early, but if one will continue, the answer will be close to this. So one will find that 0 is equal 0.13, the minimum. We know that actual minimum is literally 0, but with this algorithm, with this tolerance limit will be off by a few tenths of the argument. And this is how the optimization algorithms are functioning, and it is what we will be doing in the lab tomorrow in the evening. Thank you for the questions. Meeting is done. Looking forward to see you on Wednesday. And please consider to, and it is what we will be doing in the lab tomorrow in the evening. Thank you for the questions. Meeting is done. Looking forward to see you on Wednesday. And please consider to send to my email points by midnight of Wednesday.
Excuse me, if you want to send your email, should send to your Gmail. Which one do you check, or academic email?
dqn@gmail.com. I check it most often.
And the previous,
You send wherever you like, but I check dqn@gmail like every 5 minutes, and others I check maybe like twice per day.
okay. So I sent previous homework to your academic email. I should send you again
If-
Gmail.
Did you got? Did I answer that I got?
No. I will send you to Gmail again.
Okay. Okay. Thank you. I'll show you.
Do you want outage management or?
I don't think so. We will.